Okay, hello everybody. So today we're going to begin our discussion in Chapter 8, Section 1. And what we discuss in Chapter 8, Section 1 are sequences and series. And so over the next couple of videos, you'll understand what is meant and the difference between sequences and series and how they're used in mathematics. So it says in mathematics, the word sequence is used as much of the same way as ordinary English. Saying that a collection is listed in sequence means that it is ordered so that it has a first number, a second number, and a third number, and so on. So two examples are 1, 2, 3, 4, and then 1, 3, 5, 7. So those are sequences, and it says mathematically you can think of a sequence as a function whose domain is the set of all positive integers. Now, the way that we define a sequence is we use this generic notation a sub 1, a sub 2, a sub 3. And what you see here, a sub 1 will refer to the first number in the sequence, a sub 2 will refer to the second number, and so on. And most of the time, these sequences are infinitely long, meaning they go on forever. So you can have a sub n, which represents the nth term in the sequence. And what you can see specifically is the subscript here, the 1, the 2, the 3, the 4. It is notating what number that is in the sequence. Now, there are two types of sequences. There are infinite as well as finite sequences. So some sequences stop, and if they stop, they're called finite. If they continue to go on, they are called infinite. On occasion, it is convenient to begin the subscript with a 0. Sometimes you'll see that. So you can see here a sub 0 is indicating the first term in the sequence, and then we have a sub 1, a sub 2, a sub 3. The standard is normally a sub 1 means the first one, but like I said, on occasion you will have a sub 0 that will indicate the first number in the sequence. So the first thing we want to do here, for example 1, is to simply write the terms of the sequence. And you can see that we have a generator right here that will give us whatever term we want in the sequence if we put in the number of term that we want. So it says a sub n is equal to 3n minus 2. So they want the first 4 terms, so we will want to get a sub 1, a sub 2, a sub 3, and a sub 4. And the way that you get all of those is to put the numbers 1, 2, 3, and 4 into our formula. So in this case, it's 3 times the n minus 2, and that will give us 1. The next one is 3 times 2 minus 2, which will be 4. The next one after that is 3 times 3 minus 2, which would be 7. And then the last one, for the fourth term, we're going to stick the number 4 in for n. 3 times 4 minus 2, which would give me 10. So you can see the numbers in our sequence would be 1, 4, 7, and 10. And this sequence would go on forever. So this is an infinite sequence. Now here's another example. This says the first 4 terms of the sequence are given by a sub n equals 3 plus negative 1 to the nth, r. So they want us to find the first 4 terms. So once again, we'll do the same thing. A sub 1, a sub 2, a sub 3, and then a sub 4. And we will plug in 1, 2, 3, and 4 in for n and get our answer. So we have 3 plus negative 1 to the first. In this case, 3 plus negative 1 to the first, negative 1 to the first is negative 1 plus 3 gives me 2. The next one is 3 plus negative 1 to the second. And negative 1 to the second ends up being positive 1. 1 plus 3 is 4. Now for the third term, we will also plug in 3, but what you're going to see, put the 3 in the wrong place, there should be a 1 there. What you're going to see is we will kind of circle back and it will be the same as the first term. We have negative 1 to the third power, which is negative 1. And then when you add that to 3, you end up with 2. So once again, we come around with 2 again. Now a to the fourth, I think you'll begin to see the pattern here. Negative 1 to the fourth power is positive 1, and positive 1 plus 3 is 4. And so this would also be an infinite sequence, but it would be a sequence where we just have two numbers repeated over and over again. It would be 2, 4, 2, 4, 2, 4. And that's because what is being taken to the power is simply negative 1. So there are the first four terms of that sequence. So it says simply listing the first few terms is not sufficient to define a unique sequence. The nth term must be given. So what they're saying here is I can't just say, just list two or three numbers and then put a dot, dot, dot after it, because there are multiple ways for that sequence to go. So as an instance, you can see right here, I have 1/2, 1/4, 1/8. I can also have 1/2, 1/4, and 1/8 here. But these end up being two completely different sequences, because this one is made by being 1/2 to a power, whereas this one is made by having 6 divided by a pretty involved algebraic expression there, you see, n plus 1 times n squared minus n plus 6. So the point of this is that you cannot define a sequence by just listing numbers and then putting a dot, dot, dot after it. You actually need to write the formula for the sequence down. So it says some sequences are defined recursively, and it says to define a sequence recursively, you need to be given one or more of the first few terms. All other terms of the sequence are then defined using the previous term. And a well-known recursive sequence is the Fibonacci sequence. And then what I would like you to do is go ahead and click on this link that will explain the Fibonacci sequence to you. So another type of notation that you may or may not be familiar with is something called factorial notation. And factorial notation is pretty important for sequences in mathematics. Involve terms that are defined with special types of products called factorials. Now, the factorial is simply an exclamation point. You can see it right there. But in math, we don't call an exclamation point. We call it a factorial. And there is a button on your calculator, which I will show you later how to use that button, but that button is a factorial. So as an example, when you have n factorial, you simply do 1 times 2 times 3 times 4 all the way up to the number that you have. As a special case, note that 0 factorial is defined as 1. It is not 0. So here are some values of n factorial, just as an example of how this works. So 2 factorial is equivalent to 1 times 2. 3 factorial is 1 times 2 times 3. And 4 factorial is 1 times 2 times 3 times 4. So you can see that these numbers actually will get very large very quickly because of the nature of what a factorial is. So this says write an expression for the apparent nth term, a sub n, of each sequence. So we'll start, the first way to do this is to start by labeling each one of these. So I'm going to call this a sub 1, a sub 2, a sub 3, and then a sub 4. And what we need to do is we need to come up with a way to define these numbers. Now, in this first one, you can see that it starts with 1, then it goes to 3, then it goes 5, then it goes to 7. So this one's pretty easy to figure out because we have our starting number, which in this case is 1, and then we have the value that it changes by. It is changing by 2 each time. So what we would need to do then is to come up with an equation to show that. So when I plug a 1 in, I get 1, and when I plug a 2 in, I will get 3. And when I plug a 3 in, I will get 5, and so on. And so I think the best way to do this would be to define this as a linear equation, because it is starting and then changing by the same amount each time. So you can see the changing amount would be 2. It is increasing by 2 each time. The last thing we would have to do is to define what the starting number is. Now you may think it was 1. You may think, okay, this thing starts at 1 and changes by 2. But if I wrote it this way, a sub n equals the change, which is 2n plus 1. When I do put a 1 in here, I end up with the number 3. So that is not going to be how much or the number that we should start with. So rather than having it plus 1, we would want it to start as minus 1, just like that. So whenever I plug a 1 in, so if I want a sub 1, I can plug a 1 in. And you can see I get 2 minus 1, which is 1. If let's plug a 3 in. So if I want a sub 3, I can put 2 times 3 minus 1, which gives me 6 minus 1, which gives me a sub 3 is 5. So there you go. You can see that this did work like we expected. And so this right here is the expression for the nth term. Now the next one is a little bit trickier. Okay, so we're going to start this one, and you can see that I started to label this as a sub 1, but in actuality, what we want to do for this one is we want to start it with a sub 0, and then go with a sub 1, a sub 2, a sub 3. Now, you'll see why here in a second that we're going to do this, but the next thing that they like to do sometimes is to utilize the squares. So if you would write out the perfect squares, 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. Now, hopefully, by writing out those squares, you can begin to see the pattern of what we're doing here. That the 2 is exactly 1 bigger than the 1. The 5 is exactly 1 bigger than the 4. The 10 is exactly 1 bigger than the 9. So what we have here is we have an instance where the numbers in our sequence are 1 bigger than the perfect squares. So in order to write the perfect squares, you would simply take the n and square it, and then we said that they are 1 bigger than the perfect squares, so we'll make it n squared plus 1. Now, just to try out that I did this correctly, we have, let's try a sub 1. So if I wanted to figure out a sub 1, that would be 1 squared plus 1, and that would give me 2. And you can see a sub 1 is indeed 2. A sub 2, if I plug that in, I would have 2 squared plus 1, and that would give me 4 plus 1, which is 5. And that would also work, a sub 2. So we come up with an equation to give us the nth term of our sequence. So as you can see, some of these can be really easy, like you saw in part A, and some of these can be pretty difficult, like part B. And you may not even be able to figure them out just by looking at the sequence. So here's another example, and prior to me showing you the example I just did, I talked about having these sequences that are sometimes recursively defined. And what recursively means is you need the previous term to know what the next term is. And that's what this one is. This is a recursively defined sequence. And you can see here that they gave us the first term of the sequence, and then they said that if I want a sub k, which is any term in the sequence, I need to take the term that is right prior to it and multiply by 2 and then add 1 to it. So these are a little bit tricky to understand. If I want a sub k, which is any term in the sequence, I need to take the term in the sequence prior to it, so a sub k minus 1. So take the one right before it, multiply it by 2, and then add 1, and you'll have your next term. So that's how this sequence is formed. So this is saying if I want a sub 2, so I'm putting a 2 in for k right there, then I need to take 2 times a sub 2 minus 1 plus 1. Well, that means 2 times a sub 1 plus 1. Now, what is a sub 1? A sub 1 is 3. So I will put the number 3 in there, and you'll see I'll get 7. So the second term in the sequence is 7. So we started with 3, and now we have 7. Now if I want to find the next term, a sub 3, that's equal to 2 times a sub 3 minus 1 plus 1, which is a sub 2 plus 1. So a sub 3 minus 1 becomes a sub 2. So I need to know what a sub 2 is to figure out the next term. Well, we just figured out a sub 2. A sub 2 is 7. And so we can substitute in a 7 right there. 2 times 7 plus 1. That's 14 plus 1, which is 15. So the next term is 15. So in case you're not kind of catching on to what this is saying, it's saying take the previous term, multiply it by 2, and add 1, and you will have the next term. So if I multiply this by 2 and add 1, I get 7. If I multiply this by 2 and add 1, I get 15. If I would take that and multiply it by 2 and add 1, I would end up with 31. So we would do that one more time, multiply by 2 and add 1, and we would end up with 63. And there's the first 5 terms of that sequence. Okay, that's what I have for you today, guys. Thanks for listening. And as always, if you have any questions, feel free to email me. Have a great day.